All right, so in this video, we're going to go ahead and go into the next section, which is 5.4, optimization. Now, I know earlier this year I was saying that section 4.3 with related rates, I said that was one of the hardest topics that you're going to see in calculus. This, I would go ahead and put it up there with it. All right. I was looking through old AP exams, and it doesn't look like there's that many optimization problems, but it is a very important concept that's taught in college, and it kind of ties everything together, and it really builds off of what we've been doing in the previous sections about finding maximums and minimums. And the reason for that is because when you think about optimization, you're ultimately trying to maximize or minimize something, right? So, I mean, I guess I'll just write that here. Like, you're trying to maximize or minimize something. And essentially, you're just going to find optimal values that'll get you there. And by optimal values, I'm basically talking about the critical numbers. All right? So that's essentially what we're doing. And we're just going to really try to put that into context. I know in calculus we've done so much of what I like to call naked math, where you don't basically just use a bunch of rules, follow a bunch of steps for math that has no context. Well, this is kind of a section that actually puts it in context, and they'll be a little bit challenging. You'll see. So let's look at the first one. All right, it says find two positive numbers such that the sum of the first and twice the second is 64, and whose product is a maximum. All right. So first, what I'm going to do, I'm going to go ahead and just kind of define what variables I'm going to be using. I'll just go ahead and use x as the first number, and I'll use y as my second number. All right. So one of the things that they've already given me, and this is just an algebra 1 question, the sum of the first and twice the second is 64. So we kind of already know that x plus 2y is equal to 64, right? And ultimately here, what they're saying is that they want to see that xy, or x times y, they want to maximize this. Okay? So what we're going to go ahead and do is we're going to follow these steps up here, right? So first of all, draw and label any constants and variables for unknowns. Well, there isn't really that much to draw here. But what they want you to do is write the primary equation, or the equation that gives the formula for the quantity to be optimized. All right, so ultimately, we're just trying to find a function. We're going to go ahead and write this function as x times y, and this is what we're ultimately trying to maximize. And if you remember from the previous section, like if you want to find the maximum of anything, you set this derivative equal to 0, and then solve for those critical numbers. But the thing is, one of the things that we always want to try to do is we want to try to write this only in terms of one variable. Like here, if we did x times y, well, and we're taking the derivative with respect to x, we're going to end up with a whole bunch of dy's over dx's, and that's not necessarily something we want to do. So what I'm going to try to do is go ahead and write this function in terms of like one variable, and that's what I'm saying like in the third step. Identify the constraint and write the secondary equation. So this is our primary equation that we're going to be working with, because this is what we're trying to find the maximum of. But over here, we're going to think of this as our secondary equation, because this is what's going to help us write this in terms of only one variable. All right. So I'm going to go ahead and look at this equation and say, okay, well, I'm going to write everything in terms of x. So here I'm going to try to get y by itself. So if I subtracted x on both sides, I'm going to end up with 64 minus x, and then eventually divide both sides by 2. All right. So now I have y by itself, and I can go ahead and get this and substitute it into that y. So I know that f of x is equal to x times 64 minus x over 2. So when I go ahead and distribute my x into that function, I'm left with f of x is equal to, I distribute it into the numerator, so that'll be 64 minus x squared over 2. Okay? So like I said, this still represents the function that we're trying to look for. This still represents the I was about to say area, but yeah, but basically the x times y that we're still trying to maximize. So in order to find the maximum of this, I'm going to go ahead and take the, well, actually, I'm going to rewrite this instead, because that doesn't look like a fun thing to take the derivative of. Oh, and that's supposed to be 64x. Sorry. So again, if you have multiple terms on the top and only one term on the bottom, I can break this up as a fraction. So that'll be 64x divided by 2 is 32x. And then minus, and I'll just write this as 1/2 x squared. All right, now I'm finally going to take the derivative. So f prime of x is equal to 32 minus the power rule. That'll just lead this to be x. Yeah, that's it. It'll just be x. And then I have to ultimately set this equal to 0. So 32 minus x. So if I added x to both sides, I end up with x is equal to 32. All right. So right there, that's my critical number. And I can, if you want, I can actually sit here, and eventually you will have to do this, is you'll have to go ahead and, maybe write out the critical number, find a value below it and above it that will make this derivative and plug it into the derivative function. Like, for example, if I plugged in a value below 32 or a test point, like maybe 31, that'll give me a positive value. And if you put in 33, I'll get a negative value as a test value below that. So I'll have, increasing, decreasing. So there I have a max, right? This one was pretty simple, but, and I almost feel like I didn't even have to do that. But yeah, essentially this critical number is a maximum, and that's what they're trying to do. Is figure out what would lead to a maximum value of x times y. So I know x equals 32 will give me that, but I also want to know what the second number is. So y is equal to, from the original function, I have 64 minus x, which we now know is 32, over 2, and that's 16. All right. So the two numbers that will lead me to get a maximum value of x times y is, so I'll just say the two numbers are 32 and 16. All right. So again, typically with these optimization problems, you're always going to have a primary equation, right? This is our primary equation that we're going to try to maximize or minimize. And then we're also going to always have some kind of secondary equation, that's going to help us rewrite our primary equation in terms of only one variable. All right, and because ultimately, when we're trying to take the derivative of this and trying to find the maximum or minimum values with the critical numbers, writing it in terms of one variable is what's really going to help us. So let's actually look at one that has a lot more context. All right, so this one says a rancher plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? So essentially we're dealing with the rectangle here and only three sides of it, because, they have the river right here. And then over here they have some fencing, right, along some kind of pasture. And again, along this river, so if they're going to have fencing around the perimeter of this, we don't really need the fencing around here. So we're only going to be working with like three sides of that rectangle. Okay, and I'll just go ahead and use the vertical as y and the horizontal as x. Okay, so ultimately what they're saying, they want to require what is the least amount of fencing, right? So what we're essentially trying to do, and if we're thinking about fencing, you have to, think about this in context. We're essentially talking about the perimeter of that, right? Because the distance around that is the perimeter. So what we're trying to do is we're trying to minimize what that perimeter is. All right. So I think obviously it'd be pretty appropriate to go ahead and write out the perimeter equation. The perimeter equation in this case would be y plus x plus y, or I can just simplify that as x plus 2y. Right? So, and this is what we're trying, this is like I said, this is going to be our primary equation that we're going to try to take the derivative of. Right? But ultimately, again, I have an x and a y, so I have two variables to work with there, and I do not want to do implicit differentiation with all of this. So I'm going to have to think about a secondary equation that I can use in this problem. So if you notice, they went ahead and said that the pasture must contain 180 square meters in order to provide enough grass. So I guess a secondary equation that we can use is the area is equal to, well, the area of a rectangle is x times y, right? They told us that the area of this has to be 1,800. So I'm going to go ahead and write, not 1,800, 180,000 square meters. So we know that 180,000 is equal to x times y. So this is really going to help us write everything, rewrite this equation, but in terms of one variable. Because if I got y by itself here, I would get y is equal to 180,000, divide both sides by x. And now this I can substitute back into the perimeter equation, and I'll finally have everything in terms of one variable like I want. So that's what I'll do. I'll substitute this inside of the y, so I have p of x is equal to x plus 2, and then my y is 180,000 divided by x. So I'm going to go ahead and, I want to write this in a nicer way so that I can write the derivative easily. So that'll be x plus 360,000 divided by x. And you know what? I'll just go ahead and, I wish I had my sticky notes with me, but I know that this is essentially going to be 360,000 x to the negative 1, right? So if I took my derivative of this, well, the derivative of that will be 1. And then if I took the derivative of that, that'll be negative 360,000 times x to the negative 2, which will pretty much be minus 360,000 over x squared. Okay, so this is what I have to go ahead and set equal to 0. So I'm going to have 0 is equal to 1 minus 360,000 over x squared. And I'll kind of, rush through this next step because, I'm pretty sure we can add, we know how to add this to the other side and get x by itself. So when I go ahead and do that, I'll cross multiply and I'll have x squared is equal to 360,000. So we know that x is equal to plus or minus the square root of 360,000. So I know that x is equal to plus or minus 600 meters, right? And this is where you have to think about, I mentioned here that, you want to differentiate and find critical values within the domain, right? Well, negative 600 meters, you can't really have a negative distance. So it's really just 600 meters, all right? So it's positive because of domain. I'll just write it simple like that. Okay, so I know that x equals 600 meters, so then that means that our y is going to be 180,000 divided by 600, which is 300 meters, right? Now, okay, I'm going to go ahead and do this now, but what I should have done too was I also should have checked that this actually is our minimum value. So if I go ahead and I plug this into, or if I, use my little wiggle graph and I have 600, right? I got to go ahead and pick a value below 600. I'll just probably pick, maybe 100. And if I plugged in 100 into this, then I'll end up with a negative value. But if I plugged in, for example, maybe 700 into this, I'll end up with a positive value there. So you'll see that it'll be decreasing and increasing. So I do, in fact, have a minimum value. All right, so the pasture measures 300 meters by 600 meters. Or I should say the pasture must measure to use the least amount of fencing. Now, I'm not entirely sure. I was just kind of looking at the textbook, I'll be honest, when it comes to this one. I'm not entirely sure if writing it in context is 100% necessary. They're probably just looking for this. If you were to answer this on a free response question, but I'm just writing it in context because the textbook says it. I'm going with that for now. All right. Example number 3. Okay, so this one is saying an open box is being constructed from a piece of sheet metal 18 inches by 30 inches by cutting out squares of equal size from the corners and bending up the sides. What size squares should be cut to make a box of maximum volume? What is this volume? So I'll try my best to go ahead and draw this. So I have basically a sheet metal. right? It's the best I can draw. And then they're saying that what they want to do, so this right here is 18 by 30. All right, 30 right there. All right, and they're saying what they want to do is they want to cut out little squares in each corner. Little squares in each corner of size x by x. Okay, so that they can eventually, kind of fold these sides right here and then kind of create a box or like an open top box. This is a very popular optimization problem. I see this all the time. All right, so let's see. And they want to say, what are they trying to do? They're trying to maximize that volume, right? Well, I know that our volume equation, right, is usually length times width times height. So I probably need to figure out what is the volume of this box right there. So obviously I have my length and width, and if I were to fold this box up, that height would be the value of x. So I at least know that the height is x. So let me just say, I'll just write my height first. So my height is x. Then I got to multiply this by the length and the width. So the length and the width of that box, well, if the whole thing was 18 here before, then this length over here is going to be 18 minus x minus 2 x's, right? So that'll be, I'll just use that as my my width. So x times 18 minus 2x. And then my length, if I think about this, if the whole length is 30 minus 2x, that's going to be my length. So 30 minus 2x. So I'm going to multiply this by 30 minus 2x. Okay. And I'll just go ahead and FOIL this. So I kind of already did this earlier. So when I did FOIL it, I ended up with 4x cubed minus 96x squared plus 540x. All right. So again, if the volume is what I'm trying to maximize, now I don't think in this one I really needed a secondary equation. This one was pretty simple. I already have everything in terms of 1x. So the secondary equation wasn't necessarily needed for this one. So I'm going to go ahead and take the derivative of that, and I end up with 12x squared minus 192x plus 540. And so I have to set this equal to 0. And this is probably what I would allow you guys to use your calculator for this one, but I don't have my calculator with me, and luckily I already did this. So I know that essentially I have x is equal to 3.641, and you would have also gotten 12.359. Now, however, this doesn't really make any sense, because if the whole thing is 18 on this length, and I'm supposed to cut out two little squares here with dimensions x by x, well, if x was 12.359 and I cut that out, then 2 of those wouldn't even equal the whole thing, or like this whole length right here. And same thing over here. Well, actually, it would work for this one, but for this one, it wouldn't work. So if this is not in our domain, right, because our domain has to be like, these x values have to be less than at least half of that, right? Half of 18 is 9, so it can't be greater than 9 if you think about it logically. So it definitely has to be this one. So I'm going to do what I haven't done in the previous problems, and I'll go ahead and check to see if that actually is a maximum value. 3.641. If I plugged in a value just below that 3 and I plugged that into my derivative equation, I would end up with a positive number. You can prove it to yourself. And if I plugged in 4 into this, I would end up with a negative number. So if I'm increasing and then decreasing, then this in fact is a maximum value, right? So they say what size squares should be cut to make a box of maximum volume. So I know that the squares have to be 3.6 by 41 by 3.641, and then they're asking what is the volume. So I might as well just plug this into my original volume equation. So the volume when the x values are 3.641, that is going to be equal to, and if you put that in your calculator, you should get 886.552 inches cubed, right? So I'll go ahead and write this in context. By cutting squares of size 3.641 inches from each corner. or I'll say inches, no, not inches squared, it's just inches from each corner of the sheet metal. The volume of the box can be maximized to be 886.552 inches cubed. All right. I'm not an English major. I'm not going to pretend that I'm a good writer. However, I think that pretty much addresses everything we need. So now let's look at example 4. I should have warned you. This is going, well, I mean, you probably will see, but this is going to be a long video because optimization requires a lot of work. And I want to make sure that you guys understand this as much as possible. So for example 4, it says, what are the dimensions of an aluminum can that can hold 40 inches cubed of soda and that uses the least amount of aluminum? Okay, so we're thinking about two different things here. They're saying that can hold 40 inches cubed. So there we've got a volume, and that uses the least amount of aluminum. Well, that kind of means we want to minimize, we want to minimize like the area around the, the material, right? Or around the volume of that cylinder. So we want to minimize that surface area. All right, so try my best to draw the nicest looking cylinder I can think of. So I have a circle down there. We got some lines and pretty much another circle down here, but the top is dotted. And then that will be dotted there. So I have a radius and I have a height, right? I don't know if they're going to give you the formulas embedded into the question. I know on the semester exam they would, but on the AP exam, I'm going to try to see if I can find some, but hopefully they do. And if not, well, we should know from geometry days that the surface area is equal to 2 pi r squared plus 2 pi r h. And the volume is equal to, what was the volume? It was pi r squared h, and in this case, it's 40, okay? So now when I take the derivative of SA, what I'm going to try to do is get everything in terms of just one variable. So I'm going to look at the volume, and this our secondary equation, the volume is going to help us do that. So what I'll try to do is get h by itself and then write everything in terms of r. I feel like that's going to be the easiest one to do, or the easiest variable to work with. So if I got h by itself here, I'm going to end up with h is equal to 40 divided by pi r squared. And then this, I'm going to go ahead and substitute into that h right there. So I'm going to go ahead and say, so if I'm writing everything in terms of r, I'll just say that the surface area with respect to r is equal to 2 pi r squared plus 2 pi r, and then h we know is now 40 over pi r squared. All right, well, the pi's will cancel. One of those r's will cancel. And so I'm essentially left with s of r is equal to 2 pi r squared plus, and it's pretty much just going to be 80 over r. All right. And of course, I know that 80 over r is like saying 80 times r to the negative 1. So when I take the derivative of this, power rule here, that'll be 4 pi r. And then that's going to be negative, and then that'll still be 80 over, and then if that's going to be r to the negative 2, it'll be r squared. All right. So now I took my derivative. I got to set this equal to 0. So 0 is equal to 4 pi r minus 80 over r squared. And so I'm going to go ahead and add this to the other side. So I have 4 pi r is equal to 80 over r squared. And so let's see, I'll have r cubed is equal to 80 over 4 pi. And so essentially r is going to be equal to 1.853 inches. Okay. So now I got to go ahead and I'm just going to double check, make sure that that actually is a minimum value. So I'm going to do 1.853 there. I'll pick a value below that. If I pick maybe 1.7 and I plugged in 1.7 into my derivative function, I will end up with a negative value. If I plugged in 1.9 and put that into my derivative function, I'll end up with a positive value. So decreasing, increasing, we do in fact have a minimum there. All right, so if I know that 1.853 is our minimum, I'm going to plug that into our h, because they're asking what are the dimensions. So I know that my radius is going to be 1.853. My height, my resulting height is going to be 40 divided by pi times 1.853 squared. So then my height is going to end up being 3.708 inches. All right, so you can look at my filled in notes if you want me to write out the context for that. But those are our two answers. Height is equal to that, and radius is equal to that. All right, let's go ahead and look at the next problem. I think, the next three. Okay. So now for this one, it says, which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So this is another style of problem that I always see from like old previous exams, and I want to make sure you're ready for it. So first of all, if I want to know what is the distance between this and, or the minimum distance, because I mean, obviously, like that's not going to be the, like like these 2 points are definitely not closest to each other when it comes to like the distance between this point and any point in the graph. It might be maybe this one right here, right? I mean, is it 3, 1? I don't know, but let's or like I don't know which if this point is or 3, 1 is going to be the one that's closest to it. But what we can do is we can use optimization with this. So I know that the function is, is such, and then the point is still going to be 0, 2, but essentially we got to go ahead and use the distance formula for this. So I'll just write this distance, and I'm just going to write the distance formula the way we're used to seeing it. It'll be x2 minus x1 squared plus y2 minus y1 squared, right? So I know I'm finding the distance between this function and that point. So I know that our point is 0, 2, so I'll just go ahead and plug 0, 2 into our formula. So we'll have d of x is, I'm just going to leave this in terms of x. So I know x of the first function minus the 0 squared plus, and then I'm going to be y minus 2 squared. All right. Now, the thing is, and I'm essentially doing the distance of the function minus the point in this formula. But the thing is, I want everything in terms of one variable. And you probably already guessed that I'm going to write everything in terms of x, because I could just get this secondary equation and plug it into my primary. So I have d of x is equal to the square root of x. I could just, x minus 0 is just x squared. So I'll just write it like that. X squared plus, and then my y is 4 minus x squared, which I substitute into that, minus 2 squared, right? So now I'm just going to go ahead and simplify this. I have x squared plus 4 minus 2 would be 2 minus x squared squared, all square rooted. And then this is the boring part. I have to do all the algebra. So that'll be x squared, and if I were to multiply all of that out, 2 minus x squared times 2 minus x squared, that will just be plus 4, let's see, minus 2x squared, minus 2 minus 4x squared, and then plus x to the 4th. All right. Combine like terms. So then I have d of x is equal to the square root of, I have x to the 4th, minus 3x squared plus 4. All right. That was a bit annoying. So now I got to go ahead. So now that's my distance formula in terms of only one variable. I'm going to take the derivative, and I can do chain rule, because if this was all written to the power of 1/2, then the 1/2 would come to the front. Keep the inside. Subtract 1 from the exponent. Multiply by the derivative of the inside, which is 4x cubed minus 12x. I don't know why I put 4. No, so then that will be 6x. Yeah, there we go. Sorry, that should have been squared. So then, now my derivative. So now again, I know I got to set my derivative equal to 0. So I'm going to put 0 is equal to, and I'll put that in the denominator. So I have 4x cubed minus 6x over 2, and then that'll be square root of all of this mess. Okay. All right. So I know I already did this problem ahead of time, as you may have guessed. And I know that this bottom, there's nothing that's going to make that 0. So I have no critical points here. All right. But now I can go ahead and set the top equal to 0. And if I do that, I have 0 is equal to, I'm going to go ahead and just factor that out already. I'm going to have 2x times 2x squared minus 3. So if I go ahead and set each of these equal to 0, I'll have x is equal to 0 and plus or minus the square root of 3 over 2. All right. I don't feel like I have to show that. I think you guys know how to do the basic algebra for that. So now I have 3 critical numbers that I'm working with here. So I have 0, I have negative radical 3 over 2, and then I also have positive radical 3 over 2. Right? This seemed like it was going to be a simple problem, but it wasn't. There's just a lot going on here. So, again, I'll trust you guys to go ahead and pick the right test values to plug it in and figure out which ones are negatives and positives. So I know that it's decreasing here. If I plugged in a test value below that, it'll be increasing here. If I pick the test value between those two, it'll be decreasing and increasing there. So decreasing, increasing, decreasing, increasing. I know right here I have a minimum value. Here I have a max. And here I have a minimum value. Right? So, I mean, I have like 3 different, and this is why you always should check, because, I mean, the whole point is they want to know which one is closest. So they want to minimize the distance, right? Minimize the distance. So obviously the 0 at this point, that's probably gonna maximize the distance between 0, 2 and that function. So we definitely don't want to do that. So what we're gonna go ahead and do is if we know that these are our minimum values, they're asking which points. I didn't mean to cross it off, but they're telling us which points on the graph that is. So I'm gonna plug this back into my original function. So I know that original f, not f prime, but f of plus or minus radical 3 over 2. If I plug either of those into there, I'll have 4 minus, parentheses, plus or minus. And I mean, even though I should do 1 plus or negative, I know if I'm squaring it, it'll be positive anyways. And that'll be 5 halves, right? So the points on the graph closest to 0, 2 are negative radical 3 over 2, 5 halves, and positive radical 3 over 2, 5 halves. Okay. All right. So let's keep going. I'm looking for the problems that are most commonly asked. All right. And you'll always see problems like this. And on the problem set, I even emphasize these style of problems too. Okay, so it says over here, a rectangle has its base on the x-axis and its 2 upper corners on the parabola y equals 12 minus x squared. What is the largest possible area of the rectangle? So here I'm going to go ahead and have, so they said that there's a rectangle, a rectangle on the x-axis here, the base of it is on here. And they say that so that's a parabola facing down. So with the y-intercept at 12, it's going to be a parabola facing down. All right, and they say that there's a rectangle. The base here, I'll just go ahead and draw the best rectangle I can think of. Okay. All right, so this one you gotta think about it a little bit more. So now I gotta say, okay, well, what variables am I going to use? Well, I know that if I think of this point as like a point x, y, right? That's almost like saying that this rectangle here is has a distance of x over here and a height of y, right? Or like I'm talking about just half of the rectangle. Okay? And then obviously this is a symmetrical function, so this rectangle would be identical to this one, even though it doesn't look like that with my drawing, but this also has a distance of x and that has a height of y, right? So I'll go ahead and just kind of think about it in terms of like one rectangle. One rectangle is x times y. So then the area of the whole rectangle would just be 2 times that. So I know that the area of my rectangle in this case will be 2 times xy, right? And again, if what they're trying to do, what is the largest possible area? So we want to maximize the area. So we're gonna find the derivative of the area and set that equal to 0. But again, I have two terms right there that I don't want to deal with, but I know that y is equal to this, so I'll substitute that in there. So I know that my area, or I'll go ahead and write this as my area function of x, is equal to 2x times 12 minus x squared. So when I go ahead and multiply that out, I end up with 24x minus 2x cubed. All right, so if I want to maximize the area, I'm going to set the derivative equal to 0. So I'll just go ahead and do that now. So 0, well, fine, I'll be good. So the derivative is 24 minus 6x squared. Set that equal to 0. And I can factor out a 6 out of both of those. And then I'll be left with 4 minus x squared. And hopefully we remember our factoring well enough to remember that that's difference of squares. All right, so I know that x is equal to 2 and negative 2. All right, so obviously, I'm just going to focus on 2 right here because negative 2, as far as like the distance, you can't really say that a rectangle has a dimension of negative 2, right? So you got to also think about what makes sense and what's in your domain. So I'm going to go ahead and just double check and see that 2 works. If I plugged in 1 into this function, I'll end up with a positive number. If I plugged in 3 into this, then I'll end up with a 3 squared 9. Yeah, that'll be a negative number there, right? So I know I'm increasing and decreasing, and this, in fact, is a maximum value. So what was the question even asking? It was saying, what is the largest possible area? So I know that the dimension of x is 2. So if all they're asking for is, they're not even asking for the y, they just want to know what is the area, I'll just plug 2 into my area function. So a of 2 is equal to, let's see, 2, x is now 2 now, times 12 minus 2 squared is 4. And that'll be 4 times 8, which is 32. There you go. So the maximum area under that curve is 32 units squared. You write the sentence. I'll move on. All right. The two towers are 30 feet apart. This is the last one for the notes. What time are we on? Wow, 37 minutes. Okay. So 2 towers are 30 feet apart. One is 12 feet high and the other is 28 feet high. So go ahead and just draw that right here. So I have, I remember this one. This one's kind of a pain. So I have one height is 12 feet high and then this one is about 28 feet high. There is a stake in the ground between the 2 towers. The top of each tower has a wire tied to it that connects to the stake on the ground. Where should the stake be placed to use the least amount of wire? So I know that the distance between the 2 is 30 feet. So it was 30. And then they say that I'll just draw the stake right here, right? There's a stake on the ground, and then there's some wires that connect from the top of the building to that stake, and the top of this building to that stake on the ground. And then I'll go ahead and think of this as like, this is one wire. So I'll call that wire 1. And then here we have another wire. So I'll call that wire 2. So then it says, what is the least amount of wire. That's what I was looking for. So what is the least amount of wire? All right. So they want to minimize the total wire. And this is kind of a function that we'd have to come up with ourselves. So obviously we don't know how far away the stake is. So I mean, I'll kind of use this as x. You could put x over here. It honestly doesn't matter. It'll lead you to the same answer as long as you use the right context. But I'll go ahead and call this x, like an x distance away from this building. So then that means that this distance right here would be 30 minus x, right? So now I gotta think about some Pythagorean theorem here. So obviously W1, if I did Pythagorean theorem, W1 squared is equal to x squared plus 12 squared, which is 144. So I know that W1 is equal to the square root of x squared plus 144, right? And I know that W2, well, let's see. It'll be this squared plus this squared, all square rooted at the end. So the square root of, let's see, 28 squared is 784. I did not do that in my head. Plus 30 minus x, and then all of that squared. I'll just leave it like that for now. Okay, So I know that I'm just going to go ahead and write this out. So the total wire is going to be W1 plus W2. All right. And I know that's going to be equal to, well, pretty much W1, or the first wire. The length of the first wire is the square root of x squared plus 144 plus, and all of that, 784 plus 30 minus x, all of that squared. Okay, so I know that I'm going to write it as WT of x is equal to the square root of x squared plus 144. And I'm going to go ahead and FOIL that out. It will be plus the square root of, let's see, so over here, if I did 784 plus all of this factored out, I'm going to end up with x squared minus 60x plus 1684. You can prove it to yourselves if you want and pause it, but just take my word for it. And now I got to take the derivative of all of this, so I have to do chain. It's going to be an ugly chain rule. So the derivative of the total wire is equal to 1/2 parentheses x squared plus 144 to the negative 1/2 power times the derivative of the inside, which is 2x. So that was just this part. Plus, let's see, 1/2 times all of this on the inside, x squared minus 60x plus 1684 to the negative 1/2, and then all of that times 2x minus 60. Okay, so let me clean this up a little bit. So I know that w prime t, or the derivative of the total wire of x, is equal to, that'll come up to the top, but that 2 will cancel out with that 2. So I'll just be left with x over the square root of x squared plus 144 plus, anything I can simplify here. So I know this is going to be on the top, and if I have a 2 on the bottom, that 2 will cancel out with that 2, and that make that 30. So then I'll have plus x minus 30 over the square root of x squared minus 60x plus 1684. Okay. So that's the derivative. I don't feel like rewriting it, so I'll just set it equal to 0 there. And so what I can do, and I really did wish I had my calculator here, but what I would do is I would put this into the calculator, y equals, and then copy all of that. And if you think about it, like as far as like your dimensions on the window, I would try my best, because obviously x couldn't be bigger than 30, right? So I would say that my x min, I would leave that at 0. Because I mean, really, it could be, who knows, maybe the amount of wire would be, the least amount of wire would be like if it was like right there by one building. So you could say that x minimum is 0, but your x maximum has to be 30, right? Because if you went beyond 30, you'd have a negative distance there, which cannot happen. So if you plugged all of that into your calculator and then, did find what the 0 value was, because we're setting this equal to 0, the only value you should have gotten was x is equal to 9. So that came from the calculator. All right, hopefully by now you know how to do that. So yeah, and if we put that in context, I would say that if in reference to this tower, the stake should be placed 9 feet away from that 12-foot tower. All right. So there you go. We just kind of went through probably what was the, along with related rates, the hardest part of the derivative section, at least. All right. There's volumes around using integration, related rates, obviously. And, this is the part of calculus that really gets people scratching their heads a lot. But again, I try to go through and this video is extra long, probably reaching 45 minutes now. But I went through pretty much every style of AP problem that you would see regarding optimization. Maybe I went a little bit too fast. We did do a lot of work in this time, but hopefully it made it simple enough. So the best thing you can do is practice all of this by doing the problem set. I gave you plenty of problems to practice so that you can, be as ready as possible. So hopefully that was helpful. Keep these steps in mind and take care.